Okay, so since the last video there's been a lot of changes. The first change I'm gonna show you is this one right here. So this basically is a test for if an end is isolated and there's nowhere to go, then we can return false. Now, really simple check to implement, not very computationally expensive. It slots right into this loop that we're already doing, and this function doesn't actually do any loops or anything. It just checks the four surrounding elements, so really inexpensive to add, and it actually offers quite a boost computation wise. So it gets the time down from 507 seconds to 369 seconds for this specific board, this one right here. So this was the only 5x5 that took a while to solve, if you remember right from the last video. Now that's the last change that I made to this section of code, to this this solver, and then I moved on to trying to work on the branching factor. So the branching factor, for anyone who's not familiar, is in this recursion function. The branching factor is basically how many recursions each call is going to spawn. So in this one where we're looping over this list, we're spawning however long this list is. Like that's the branching factor, so the length of this list is the branching factor. Now, to minimize this branching factor, we need to shorten this list somehow. So how can we do that? Well, if you think about the board, so if we go over here, we don't need to create new branches for every single possible move. What we could do is just isolate one colour, so yellow, and say make a move, and then the next time we isolate a colour, it could be any colour, say it picks blue, and now it goes make a move, and now isolate a colour again, it could be red, make a move, and maybe back to yellow, make a move. And now the idea is that we're doing one at a time, so our branching factor here, it's not quite one, but it's basically however many. So you're going to pick a random colour, so say we pick yellow, our branching factor would in this case be 1 because there's only one possible move for this one. But if we pick red, our branching factor would be 4 because it's 4 possible moves here. You might notice I'm only using one end for each one. We're not going to use 2 because that again doubles the branching factor and there's no need. As I've said before, we can treat one end as static, and that helps a lot with computation. So by only considering one colour at a time, we're reducing the branching factor by on this particular board we'd be reducing it by at least half, because if you pick red, that's 4, whereas if you pick in red, blue, yellow and green at the same time, that's going to be 1, 2, 3, 7, that's going to be 11, so it's you're reducing the branching factor by 1/3 on this first move alone. So yeah, basically this is where I wanted to head. The idea is that eventually, after picking random colours and just making moves like this, you'll either hit a state where you solve it, or you won't and you'll just backtrack, and eventually you might get back to the beginning and take a different route. But the idea is all the possible routes are there, because yellow has to go here, and then say if you pick yellow again, it has to go up or right, and we're actually including both possibilities, so we are getting every board eventually, but we're just not doing it multiple times. So basically an easier way to put it is going blue here and yellow here. This produces one board. Now going yellow here and blue here produces another board. Now we don't need to check these as individual separate boards. We only need to check it once. So the yellow here and then the blue here would only produce one board in my new method, whereas the old method would have done both these moves as like separate branches, and therefore like we were checking millions of different boards multiple times, like all the different boards sometimes have been checked millions of times, and that was why the computation time just got absolutely huge. Yeah, it's pretty difficult to explain that, but if you ever read through the code and try and play around with the board, hopefully you'll be able to understand it. So, how did I implement this? I decided I would leave this code here. This is the recursive solver. This was going to be what this was. This is going to be left, and I've uploaded that to Git. So if you want to see this, this is the state it's going to be in. This code will now be left and probably not touched again. And now we're going to have a final version. So this will be the best version of the bot using all the methods. It will combine all the methods eventually. This will be where the best solver is that I have. Now, basically, it just takes the exact same functions in the previous one. Like recursive solve is exactly the same, but this time, find possible moves has this little bit at the beginning, sort of this right here, that basically just picks a colour out. Once it's picked the colour, it looks for that colour and finds all the possible, like the 4 different directions that colour could possibly go in, and adds them to the list of boards, and then that is all we return as our list of boards, the possible moves for that one colour. And then other than that, this code is exactly the same as far as I know. It's got like a little timer in here to tell you how long the computation time took for solving the board. So obviously this doesn't include in like reading the board in, because I didn't want to include that. I want to just see how long solving the actual board took. And yeah, I don't actually think there's anything else to go over in the code, because all the code is pretty much the exact same as the other one. So all I'm going to do now is show you it running for a little bit, because it's actually pretty amazing how much better this is over previous versions that I've made. So I could run this over a lot of levels and just show you it running like loads and loads of times, but I'm going to do that in a different video. There'll probably be a video coming up, I might actually put it up at the same time as this one, where it's just all the levels back to back being ran to see how long they take to run. So yeah, if you want to see that, that'll be in a separate video, but we're just going to go over like a couple of levels right now. So yeah, let's have a look. We'll pick, and yeah, you'll see all these levels are now done. It's been through them all. So we'll do 26. 26 was problematic. It took, what did I get down to, like 3 minutes or something, 370 seconds or something to solve. And this version takes, what's that, 0.009 seconds. And whoops, it's calling multiple times, stop. So yeah, 0.009 seconds as opposed to 370 seconds, so unbelievable speed increase. And thanks to that we can go do these harder levels. Now I haven't done all the 9s yet, because some of them, I think it was level 2, took like 10 minutes to run, so there is still improvement that needs to be made, and level 2 has actually been solved with my my force method. So see if we can figure out how it was solved. Maybe it needed the edge thing. Oh no, this went to here. Yeah, maybe it needed the edge one as well, but this has been solved by my other version, so when we couple them both together I'm expecting this to be solved like instantly. But yeah, that's why I haven't done all the 9s yet, but in the longer video that'll, like I said, will be uploaded with this one, all the 9s will hopefully be done, assuming they don't take like hours to run. A couple of the 8s took a couple of minutes to run as well, like one of them took 2.5 minutes or something, but the majority of them are pretty quick, like this one here. So yeah, the speed of it is pretty insane. I wasn't expecting it to be this great. Like, I thought it would solve some levels, but I thought, like, without the addition of the old code mixed in with this one, I thought it wouldn't really be that practical on the bigger boards, but it turns out it is. Like 6 seconds to solve that one there. All the 5x5s get solved in like less than 0.01 second or something, and then like the 6x6 gets solved in less than about half a second or something like that. They generally scale pretty well. This 8's taken a while. This could have been the 2.5 minute one. No, never mind, 20 seconds. There definitely was one that took a while, but I'm not sure where it was. But yeah, that's probably enough for this. Again, if you want to see the code, it's on GitHub. Feel free to run it yourself if you're interested in this. And yeah, that's probably going to be it. Next video, probably going to be looking at like mixing in the two. So putting like somewhere in this recursive loop, like the code from this one. Like the solveboard function is probably going to be implemented without the risky methods. We'll be taking those out, I think. Probably going to delete those altogether. Actually, I don't really like the idea of sometimes getting the problem wrong. So yeah, that's it for this video. If you liked the video, like it, subscribe if you want to see these other videos that I'm going to be making on it. And yeah, thanks for watching. I'll see you in the next one.